Section 4.3, triangle congruence using angle, side, angle, and angle, angle, side. First slide, postulate 4.3, which is angle, side, angle, with an abbreviated ASA. This postulate states if two angles and the included side of one triangle are congruent to two angles and an included side of another triangle, then the triangles are congruent. Here I have two triangles. I'm given triangle GBH and triangle KPN. Angle G is congruent to angle K, designated by the double arc, and I have angle H congruent to angle N, designated by the single arc, and I have a side GH congruent to side KN. We know that this is the included side because an included side is the side that is sandwiched in between the two congruent angles. So here, GH is sandwiched between congruent angle G and H, and side KN is sandwiched between K and N. Side GB and BH are non-included to these two congruent angles, and side KP and PN are non-included sides. So I can state that these two triangles are congruent because of angle, side, angle. I also can create a congruence statement, which would be triangle GHB is congruent to triangle KNP. On this slide, we have theorem 4.2, which is angle, angle, side, or abbreviated AAS. Here, this theorem is if two angles and a non-included side of one triangle are congruent to two angles and the corresponding non-included side of another triangle, then the triangles are congruent. In this diagram, I'm given angle D is congruent to angle G, represented by the double arcs, and angle C, congruent to angle X, represented by the single arc. The non-included side is segment DM, and given to be congruent to segment GT. Segment DM and GT are corresponding sides, and they are non-included. Therefore, given angle, angle, side, I can state that these two triangles are congruent by the given theorem. The other non-included side would be segment CM and TX. The included side for these triangles would be the one sandwiched in between the two congruent angles. So here, my two congruent angles are D and C. Therefore, the side is segment DC. And on this triangle, the congruent angles are G and X. Therefore, the included side would be segment GX. But here I'm given the non-included side. I could still create a congruent statement, which would be triangle. And I'm going to start with the double arc to a single arc, so DCM is congruent to triangle, and following the same format as double, single to no arc. Double would be G single XT. On this slide, we're asked to write a congruent statement for the two triangles that we can prove to be congruent, if possible. And if so, we want to state the reason for their congruence, and then write the congruent statement. Here, we're given triangle ABC and DEF. We are given two sides are congruent. DE is congruent to AC, represented by the single ticks, and we have FE congruent to AB, represented by the double ticks. We also have angles congruent, which would be angle F and B, represented by the single arcs. If I abbreviated this shortcut of congruence, that would give me side, side, angle, or also angle, side, side. That statement or reason is not a valid reason to prove triangles congruent. It doesn't represent congruent triangles. Therefore, in this instance, this would have to be impossible at this point to prove these two triangles congruent. This is not a valid definition. On my next example, I'm given angle K is congruent to angle G, and angle JIK is congruent to angle GIH, and we know that because of vertical angles being congruent. And I'm also given that JK is congruent to GH, represented by the single tick. In this instance, I know that the triangle is congruent by one of the theorems or postulates we just defined, which would be angle, angle, side. This would not be angle, side, angle because the congruent corresponding sides are non-included. Therefore, I use angle, angle, side. My congruent statement would be, if I start with Kij, congruent to triangle, and I have to use the same order on my congruent triangle here, which would be GIH. For the next example, I'm given angle L congruent to angle Q, angle P by the double arc congruent to angle N, and angle M by triple arcs congruent to angle O. That tells me that three angles of this triangle are congruent to three angles of this triangle. We have no theorem or postulate or definition that justifies congruent angles when I have three angles being congruent. What it does justify is that the angles are in proportion. But here, we want a congruence, and we don't have a postulate or theorem with angle, angle, angle that justifies that. Therefore, this is impossible. Our next example, I'm given two triangles inside of this quadrilateral. I'm given RSU, and I'm also given UTR. I know that the right angles are congruent, represented by the box. I know angle TRU is congruent to angle SUR by the single arc, and segment RU is represented in both triangles. Therefore, by the reflexive property, that segment is congruent to itself. Therefore, I am given a congruence of these two triangles by our theorem, which is angle, angle, side. And I know it's angle, angle, side because this segment RU is not the included side on either triangle. Therefore, that represents our congruence of angle, angle, side. The congruent statement would be triangle, and I can start with the right angle. I'm going to go SUR is congruent to, again, starting with the right angle going to the single arc, TRU. Our last example, I'm given congruent angles represented by the single arc, which is XYV and angle XYW. I know that YV is congruent to YW by the single tick, and I know that XY is represented in both triangles, and therefore it's congruent to itself by the reflexive property. Here, I am given side, angle, side, for the reason that these two triangles are congruent. In this situation, I have an included angle in each triangle. It's sandwiched in between the two congruent sides. Now I can create a congruent statement by saying triangle XYV is congruent to triangle XYW. And recall that side, angle, side is a previously learned theorem for stating congruent triangles. Our next example is a proof. Here I'm given AD is parallel to BC and AB is parallel to DC. That's also represented in our diagram with the parallelism represented with the arrows. I want to prove triangle ABD is congruent to triangle CDB. With parallelism, I know that I'm given AB is parallel to DC. Those two segments generate alternate interior angles. And since they are parallel, those angles are congruent. So I have angle CDB congruent to angle DBA. I also have segment AD parallel to BC. Those two parallel lines generate alternate interior angles. And since they are parallel, those angles are congruent. Therefore, I have angle ADB congruent to angle CBD. And the reason is the alternate interior angle theorem. If two parallel lines are cut by a transversal, then alternate interior angles are congruent. Step 3, I have segment DB congruent to itself. And the reason being the reflexive property. Therefore, I can now state that the triangle ABD is congruent to triangle CDB. And the reason for the congruency is angle, side, angle. And I know it's that theorem because DB is the included segment between the congruent angles. Therefore, that gives me angle, side, angle. On our next proof, I'm given that segment AD bisects BC and that the measure of angle A is equal to the measure of angle D. So in my diagram, I know that angle A is congruent to angle D. I can put arcs in there to represent that. I'm also given that segment AD bisects BC. Therefore, AD intersects at the midpoint of BC. So E is the midpoint of BC, and that tells me that segment BE is congruent to segment EC. So step 2 is BE is congruent to segment EC. And that would be because of the definition of a segment bisector. You could also put definition of a midpoint because the bisector intersects at the segment's midpoint. I also know that angle AEB is congruent to angle CED. And the reason for that is the vertical angle theorem. Which states that vertical angles are congruent. Now, I can state that triangle ABE is congruent to triangle DCE. And the reason is angle, angle, side. And it's angle, angle, side because the congruent segments are not included between the two congruent angles. Given that angle CDB is congruent to angle BEC and angle DCB is congruent to angle EBC. And we want to prove that triangle DCB is congruent to EBC. We're given multiple triangles inside of our diagram, but what we want to identify are these two triangles we're trying to prove congruent. So here I have triangle DCB, and the other triangle is triangle EBC. And if I use my given, I know that angle CDB is congruent to angle BEC. I also know that angle DCB is congruent to angle EBC. What else is given to me is in the diagram itself. I know that segment CB is congruent to itself by the reflexive property. You can see by the diagram when I separated them, segment CB is in both diagrams. Therefore, I can state that segment CB is congruent to segment CB because of the reflexive property. Now I can state that triangle DCB is congruent to triangle EBC, and the reason is angle, angle, side. And I know it's angle, angle, side because the segment in each diagram, which is itself, is not included between the congruent angles. Therefore, that gives us angle, angle, side.